The following video is on limits as x goes to infinity. We saw last time that as x goes to 0, 1 over x goes to positive or negative infinity. And one of the ways we saw this was by looking at a pizza with slices. As the number of slices got smaller and smaller, the size of each of those slices, represented by 1 over x, got larger and larger. This time, however, we're going to look at what happens as we slice the pizza into more and more slices. Just like before, we see that the size of each slice is getting smaller and smaller. So as the number of slices gets larger, each slice gets smaller. We can write this as x goes to infinity, 1 over x goes to 0. Another way to see this is to look at a chart of x compared to 1 over x. If we look at values of x getting larger and larger, we see that the values of 1 over x are getting smaller and smaller. We write this as the limit as x goes to infinity of 1 over x equals 0. This means that as x gets larger and larger, f of x is getting closer and closer to 0. Yet another way to look at this is to look at the graph. Here you see the graph of f of x equals 1 over x, and notice that as x gets bigger and bigger, or closer and closer to infinity, the y value is getting closer and closer to 0. We could also look at what happens as x goes to negative infinity. Notice that as x goes towards negative infinity, the y value is again getting closer and closer to 0. This pattern holds in general. Any non-zero, non-infinite number divided by a number that's going to infinity is itself approaching 0. Let's look at some examples. The limit as x goes to infinity of 3 over x minus 2. If we do direct substitution, we'll have 3 over a very large positive number, which we said goes to 0. Another example, if we look at the limit as x goes to negative infinity of 25 over x minus 2 times x plus 2, we notice that we get 25 over negative infinity times negative infinity. Notice that what that means is we're taking a negative number times a negative number in the denominator, so the denominator is actually going to be a very large positive number, so 25 over positive infinity, which again we know goes to 0. What if the numerator goes to infinity, though? Let's look at the following example. The limit as x goes to infinity of x minus 2 over x minus 3. Direct substitution gives infinity over infinity, which is an indeterminate form. This means that we need to use another technique. The technique that we're going to use is to divide by the largest power of x that we see in the top or the bottom. In this case, the largest power of x that we see is an x to the 1. So I'm going to divide both the top and the bottom by 1 over x. This gives me the limit as x goes to infinity of 1 minus 2 over x over 1 minus 3 over x. Now we can just take the limit piece by piece. We'll have 1 minus 0 over 1 minus 0, which ends up being 1. And we're finished. We can look at another example of finding this largest power of x. Let's look at the limit as x goes to infinity of x minus 3 over x squared minus 1. Direct substitution again gives us infinity over infinity, which is an indeterminate form. So the largest power of x in this case is an x squared. So I'm going to divide the top and the bottom by 1 over x squared. This gives me the limit as x goes to infinity of 1 over x minus 3 over x squared divided by 1 minus 1 over x squared. And direct substitution gives me 0 minus 0 over 1 minus 0, which is 0 over 1, or 0. We also have a super sneaky trick for solving these types of problems. This only works for rational functions, however. Given a rational function r of x, If the largest power of x is in the denominator, or in the numerator, the limit as x goes to infinity of r of x is plus or minus infinity. If the largest power of x is in the denominator, the limit as x goes to infinity of r of x equals 0. And finally, if the largest power of x is the same in the numerator and denominator, then the limit as x goes to infinity of r of x is the ratio of the leading coefficients. Let's look at an example. The limit as x goes to infinity of x cubed minus 5x over x to the fifth minus 3x. Here the largest power of x is in the denominator. And so, as we saw with the super sneaky trick, this means that the limit goes to 0. Let's look at the limit as x goes to infinity of x to the fifth minus 3x over 4x to the fifth minus 1. Here, the largest power of x is the same in the numerator and the denominator. So we're going to take the leading coefficients. Notice the leading coefficient in the numerator is a 1, and the leading coefficient in the denominator is a 4. So the answer is 1/4. In the third example, let's look at the limit as x goes to negative infinity of x to the fifth minus 3x over 4x squared plus 1. The largest power of x in this case is in the numerator, so we know that this should go to plus or minus infinity. But in order to test which one it is, we need to plug in a number that's relatively big and close to negative infinity. So we're going to plug in negative 100 into the top and the bottom. And we don't care what the exact answer is, we just care whether it's positive or negative. So notice that the numerator is a big negative number plus a less big positive number divided by a very big positive number. So we have a negative over a positive, which gives me negative. So our answer is negative infinity. Let's do another example. The limit as x goes to infinity of the square root of x squared minus 2 over x minus 3. Notice that the largest power of x in this problem is actually an x to the 1, because the square root and the x squared cancel each other out. So what I'm going to do is multiply the top and the bottom by 1 over x and distribute it through. In order to distribute the 1 over x into the radical, however, I need to actually square 1 over x. So I have the square root of x squared minus 2 times 1 over x squared over x minus 3 times 1 over x. Now I can distribute the 1 over x squared through the top and the 1 over x through the bottom and do direct substitution like we've been doing. And I end up with 1 over 1, which is 1. The last thing we need to discuss are horizontal asymptotes. A horizontal asymptote is what happens to y as x gets really, really large. In this case, y is going to 0. A function f of x has a horizontal asymptote at y equals c if the limit as x goes to infinity of f of x equals c, or the limit as x goes to negative infinity of f of x equals c. For example, let's find any horizontal asymptotes of f of x equals arctangent of x. The graph of arctangent of x is shown below, and we can see that the limit as x goes to infinity of f of x is pi over 2, and the limit as x goes to negative infinity of f of x equals negative pi over 2. So f has two horizontal asymptotes. One is y equals pi over 2, and the other is y equals negative pi over 2.